Dear students, in the previous video, we discussed about the vibrating system using a simple harmonic oscillator model. We solved the Schrodinger wave equation and found out the vibrational energy. Today, we will see another interesting system, a rotating system, that is the rotational motion of diatomic molecules, which is explained using the rigid rotator model. And this video is the first part of the quantum mechanical treatment of rigid rotator. Here we are considering a rotating system in one plane, which is also referred to as particle inner ring problem. First, let's see what is meant by a rigid rotator. This is a simple model for a rotating diatomic molecule. The model consists of 2 point masses m1 and m2 at fixed distances r1 and r2 from their center of mass. For example, if it is HCl, then hydrogen and chlorine atom are the 2 point masses separated at distances r1 and r2 from the center of mass, and r equals r1 plus r2. Now, why it is called a rigid rotator? The distance between the two masses is fixed. Or we can say that the internuclear bond distance does not change during the rotation. And that's why this model is referred to as the rigid rotator model. Even though a diatomic molecule vibrates as it rotates, the vibrational amplitude is small compared to the bond length. And so it is a good approximation to consider the bond length to be fixed. So we can say that rigid rotator is an idealized diatomic molecule incapable of any vibrational motion. The rigid rotator can be treated as having one mass fixed at the origin with the other rotating about the origin at a fixed distance r. So classical treatment shows that the energy of the rigid rotator is the kinetic energy, which is equal to half I omega square, where omega is the angular velocity and I is the moment of inertia, where the moment of inertia is given by mu r square, and mu is the reduced mass. So instead of 2 point masses, we are treating it as a single mass of mu, that is equal to m1 m2 by m1 plus m2, and r is the bond length, and the angular momentum is given by L equals I omega. Now when come to quantum mechanical treatment, we can represent the total energy using the Hamiltonian operator. Here the Hamiltonian operator is just the kinetic energy operator. Why? Since the bond length or R is fixed, the potential energy is taken as 0. So the Hamiltonian operator will be only the kinetic energy operator, and it is given by h cap equals minus h square by 8 pi square mu into del square, where h is the Planck's constant, mu is the reduced mass, and del square is the Laplacian operator, which is given by dou square by dou x square plus dou square by dou y square plus dou square by dou z square in Cartesian coordinates. When we deal with the quantum mechanical treatment of a rigid rotator model, we usually express the coordinates, the spatial coordinates, in terms of spherical polar coordinates instead of the normal Cartesian coordinates x, y, and z. And this figure shows the relationship between spherical polar coordinates and the normal Cartesian coordinates. So instead of x, y, and z, the spherical polar coordinates are r, theta, and phi. In this figure, the point P represents the position of the particle, and the vector r is the distance from the origin to the point P. This is the radial vector. Now we have an angle theta, and this is the angle the radial vector r makes with respect to the z-axis, and this is known as the zenith angle or latitudinal angle. Now the third coordinate is phi, And this is the angle measured in the xy plane between the x-axis and the projection of the line R joining the particle P. So here the dashed line represents the projection of the line R, which is joined with the particle P. And this angle phi is known as the azimuthal angle, or also known as the longitudinal angle. So instead of x, y and z in Cartesian coordinates, we have r, theta and phi in spherical polar coordinates. Using simple trigonometric relations, we get x equals r sin theta cos phi, y equals r sin theta sin phi, and z equals cos theta. The value of r ranges from 0 to infinity. The angle theta varies from 0 to pi, and the angle phi ranges from 0 to 2 pi. So in the Hamiltonian for the rigid rotator, we have minus h square by 8 pi square mu into del square. So while solving the rigid rotor model, we have to express del square in spherical polar coordinates. And instead of dou square by dou x square plus dou square by dou y square plus dou square by dou z square, while we express del square in spherical polar coordinates, we get del square equals 1 by r square dou by dou r of r square dou by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou by dou theta plus 1 by r square sin square theta dou square by dou phi square. Getting del square in this form from the coordinates x, y and z is a very lengthy derivation, so we have avoided those steps. If you are interested in seeing the preliminary steps, you can refer the textbook on quantum chemistry by R.K. Prasad, and you can see those steps in Appendix 1. So since it's a very lengthy derivation, we have avoided those steps. So for the time being, please remember del square equals 1 by r square dou by dou r square dou by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou by dou theta plus 1 by r square sin square theta dou square by dou phi square. Now our next step is to set up the Schrodinger wave equation for a rigid rotator and finding out the Eagen function and Eagen value. As I said earlier, the Hamiltonian operator for a rigid rotator is only the kinetic energy operator. Potential energy is 0 because R is fixed. Therefore, we can write the Hamiltonian as h cap equals minus h square by 8 pi square mu into del square. Expressing del square in spherical polar coordinates, and we get del square equals 1 by r square dou by dou r square dou by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou by dou theta plus 1 by r square sin square theta dou square by dou phi square. Now here we have assumed that r is a constant. Since r is a constant, the first term disappears. That is, the term dou by dou r of r square dou by dou r will be 0. And also, if we put r equals a, then the Hamiltonian h cap can be written as h cap equals minus h square by 8 pi square mu into, there is no first term, we are going to write only the second and the third terms. Also, we have put r equals a. So, into 1 by a square sin theta dou by dou theta of sin theta dou by dou theta plus 1 by a square sin square theta into dou square by dou phi square. We know that mu is the reduced mass. So mu into r square, which is equal to mu a square here, is nothing but the moment of inertia, which is denoted as I. Therefore, we can rewrite the Hamiltonian as h cap equals minus h square by 8 pi square I into 1 by sin theta dou by dou theta of sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square. Now looking at the Hamiltonian h cap, we can see that there is no r here. Why? Because it is fixed. It cannot vary. So only the other two angles, that is theta and phi, varies. So we can say that the orientation of a rigid rotator is completely specified by these two angles, that is theta and phi. And hence rigid rotator wave functions depend on these two variables. Therefore, the Schrodinger wave equation for a rigid rotator can be written as h cap xi equals E xi, that is minus h square by 8 pi square I, 1 by sin theta dou by dou theta of sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square into xi equals E xi. So this is the Schrodinger equation for a rigid rotator. Now we move on to the solution of this equation. Consider a special case of rigid rotation, that is plane rotation, where rotation can take place only in one plane, that is in two dimensions. And this is referred to as rotation in plane or fixed axis. This is also known as particle in a ring problem. Suppose the rotator is rotating in the xy plane. If a rigid rotator rotates in the xy plane, then the rotational axis coincides with the z-axis. Then theta becomes pi by 2. Therefore, the Schrodinger equation becomes minus h square by 8 pi square I dou square by dou phi square into xi equals E xi. We had the Schrodinger wave equation minus h square by 8 pi square I, 1 by sin theta dou by dou theta sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square into xi equals E xi. Now we have considered the rotation taking place only in the xy plane. Then theta becomes pi by 2. So if theta becomes pi by 2, then this term will be 0. The only term left will be dou square by dou phi square. Therefore, we can write minus h square by 8 pi square I dou square by dou phi square into xi equals E xi, which can be rewritten as dou square xi by dou phi square equals minus 8 pi square IE by h square into xi. And this is the Schrodinger equation for plane rotation. Now we want to find a solution for this equation. We can prove that xi equals a e raised to I m phi will be a solution for this equation, provided that m square is equal to 8 pi square IE by h square and a is a constant. Now let's see the proof for the solution. We said xi equals a e raised to I m phi is the solution. Do d xi by d phi. So this will be equal to a into differential of e raised to I m phi. I m into e raised to I m phi. Now we have to do d square xi by d phi square. So that will be equal to a into I square m square e raised to I m phi, which is equal to the value of I square is minus 1. So this become minus a m square e raised to I m phi. Now we have the Schrodinger equation. D square xi by d phi square equals minus 8 pi square IE by h square into xi. So we are substituting the value of d square by d phi square, that is minus a m square e raised to I m phi, and the value of xi, that is a into e raised to im phi. In this equation, then we get, instead of d square xi by d phi square, I'm going to write minus a m square e raised to im phi equals minus 8 pi square I e by h square into xi. So instead of xi, a e raised to im phi. So from this we get m square equals 8 pi square I e by h square. And the possible values of m is m equals 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. So thus we have proved that the solution for the Schrodinger equation dou square xi by dou phi square equals minus 8 pi square I e by h square into xi is xi equals a e raised to im phi, provided m square equals 8 pi square I e by h square and a is a constant. And that we have proved here. And we saw that the possible values of m is 0, plus or minus 1, plus or minus 2, etc. Now let's see the proof for it. In order for the probability density to be uniquely defined at every point, the wave function must be single valued. We have already discussed the conditions for an acceptable wave function. The first condition is it must be single valued. So applying this boundary condition, and since the angles phi and phi plus 2 pi represent the same point, then the property of single valuedness demands that xi of phi equals xi of phi plus 2 pi. Why? Because the value of phi ranges from 0 to 2 pi. Phi and phi plus 2 pi represents the same point. We have xi of phi equals a e raised to im phi, and xi of phi plus 2 pi can be written as a e raised to im into phi plus 2 pi. So equating xi of phi and xi of phi plus 2 pi, we get a e raised to im phi equals a e raised to im phi plus 2 pi. So this is equal to a e raised to im phi into e raised to im 2 pi. That is e raised to im 2 pi equals 1. And this is only possible if the value of m equals 0, plus or minus 1, plus or minus 2, etc. So we have proved that the value of m will be 0, plus or minus 1, plus or minus 2, etc. Now we got e raised to im 2 pi equals 1. So let's prove that e raised to im 2 pi is always equal to 1. We saw that e raised to im 2 pi equals 1. If m equals 0, then we have e raised to 0, which is equal to 1. Suppose m equals 1, then e raised to im 2 pi becomes e raised to I 2 pi. So this is equal to cos 2 pi plus I sin 2 pi, which is again equal to 1. Similarly, if m equals minus 1, then again e raised to minus I 2 pi. This will be equal to cos 2 pi minus I sin 2 pi, which is equal to 1. So m can be 0, m can be plus 1, m can also be minus 1. Similarly, m can have values 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Thus, we see that m can have only certain values, and m can be called the rotational quantum number. So from this, we can calculate the energy eigenvalue. We proved that the solution for the Schrodinger equation for plane rotation is xi equals a e raised to im phi only if m square is equal to 8 pi square IE by h square. So from this, we can calculate the energy eigenvalue. If m square equals 8 pi square IE by h square, then we get the rotational energy may represent as EM equals m square h square by 8 pi square I, where m equals 0, plus or minus 1, plus or minus 2, etc. So we have got the energy eigenvalue of a rigid rotator rotating in 2 dimensions or rotating in only one plane. Now we have to find out the complete eigen function. We already got xi equals a e raised to im phi. Here a is a constant. So we have to find out the value of this constant a. In order to find a, we apply the normalization condition. That is integral 0 to 2 pi, because phi ranges from 0 to 2 pi. Xi star xi d phi equals 1. That is integral 0 to 2 pi a e raised to im phi the whole star into a e raised to im phi into d phi equals 1. A is a constant, so a into a square can be taken out of the integral. Then inside we will be having e raised to minus im phi, because the conjugate of a raised to im phi will be e raised to minus im phi. So e raised to minus im phi into e raised to im phi, which will be equal to 1. So from this we get a square integral 0 to 2 pi d phi equals 1. That is a square into phi within the limits 0 to 2 pi equals 1. That means a square equals 1 by 2 pi, or we can write a equals plus or minus 1 by root of 2 pi. So we have found out the value of the constant a, which is given as a equals plus or minus 1 by root 2 pi. We usually take the absolute value of a, so that we can write absolute value of a equals 1 by root 2 pi. Therefore, we can represent the wave function as xi equals, instead of a, we can write 1 by root 2 pi e raised to im phi. And this equation represents the eigen function for plane rotation. In this equation, we can see that there is a factor I, which means the wave function has a complex part, 1 by root 2 pi e raised to im phi. So this equation also represents an imaginary set of wave functions for plane rotation. If m equals 0, which is the minimum possible value, then we get xi 0 equals 1 by root 2 pi. So here you can see that the wave function is independent of phi. The corresponding energy value will be 0. Therefore, the system does not have 0 point energy. Whereas in simple harmonic oscillator, when n is equal to 0, the minimum possible energy was E equals half h nu, which was called the 0 point energy. But here, when m equals 0, which is the minimum possible value, the wave function xi becomes independent of phi and the energy value is 0. That means rigid rotating system does not have any 0 point energy. If m equals plus 1, then xi1 equals 1 by root 2 pi e raised to I phi, and E1 equals h square by 8 pi square I. Similarly, if m equals minus 1, then xi minus 1 equals 1 by root 2 pi e raised to minus I phi, and E1 equals h square by 8 pi square I. So here you can see that when m equals 1, E equals h square by 8 pi square I, and if m equals minus 1, then also E equals h square by 8 pi square I. So m equals plus or minus 1 state have the same energy and it is doubly degenerate. We say that xi equals 1 by root 2 pi e raised to im phi represents an imaginary set of wave functions. By suitable linear combinations, we can get real solutions. That is, xi plus equals 1 by root 2 pi e raised to im phi plus e raised to minus im phi into 1 by root 2. For the plus combination, we have to use an additional normalizing factor which is equal to 1 by root of sum of combinations of the function. And that's why we have written 1 by root 2. We have two functions, e raised to im phi and e raised to minus im phi. So the plus combination will be xi plus equals 1 by root 2 pi e raised to im phi plus e raised to minus im phi into 1 by root 2. For the minus combination, the additional normalizing factor is 1 by I into root of sum of combinations of the function. Therefore, xi minus can be written as 1 by root 2 pi e raised to im phi minus e raised to minus im phi into 1 by I into root 2. So here we have xi plus equals 1 by root 2 pi e raised to im phi plus e raised to minus im phi. So this will be equal to 1 by 2 into root pi e raised to im phi plus e raised to minus im phi is nothing but 2 cos m phi. So we can write into 2 cos m phi. So this is equal to 1 by root pi cos m phi. Similarly here, this will be equal to 1 by I 2 into root pi into e raised to im phi minus e raised to minus im phi, and that is 2i sin m phi. So this is equal to 1 by root pi sin m phi. So we got xi plus equals 1 by root pi cos m phi and xi minus equals 1 by root pi sin m phi. Thus, for plane rotation, the Eagen functions xi equals 1 by root 2 pi e raised to im phi, where m equals 0, plus or minus 1, plus or minus 2, etc. represents the imaginary set of solutions, and xi equals 1 by root pi cos m phi and 1 by root pi sin m phi represents the real set of solutions. And the eigenvalue is given by Em equals m square h square by 8 pi square I. So we have solved the Schrodinger wave equation for a rigid rotator rotating in one plane with a fixed axis. The Eagen functions are xi equals 1 by root 2 pi e raised to im phi, which represents the imaginary set, and xi equals 1 by root pi cos m phi or 1 by root pi sin m phi, which represents the real set of solutions. And the eigenvalue, that is rotational energy value, is m square h square by 8 pi square I, where m is the rotational quantum number.